So this video is going to serve as a comprehensive everything you need to know guide on making modern high-end furniture. It's going to include buying wood from a hardwood store, milling that wood or processing it so that it's the proper dimensions for your needs, gluing the processed wood into panels, preparing the panels for finish, and subsequently finishing. There's a few explanations of this stuff on YouTube, but none of them show you how to weld. I'm going to teach you basic metal fab, at least MIG welding, for the purpose of fabricating mild steel hardware for furniture, like table legs. We're not going to get into complicated joinery. This is more for people wondering, how do I get into furniture making? Where do I get wood from? How do I make it usable? How do I make metal hardware? And how do I attach that to the wood? I'm going to be making this bench. It's one of these benches that I designed to fit motorcycle helmets underneath and planters on either side, but you can use this exact same process to make anything comprised of solid wood panels and steel legs or a steel base, from a little end table all the way up to a massive conference table. Then if you expand your skills into simple joinery like rabbets and box joints, you can make things such as these vinyl record cubbies I made. And if you expand your skills into template making and template routing, you can make more mid-century modern stuff with more rounded contours, like this coffee table. I have a video on this table and it goes into template stuff. Before we get into talking about buying wood, I'll let you know that this video is geared mainly towards Americans. Everything is applicable to Europe and elsewhere, but I don't use the metric system, and neither do the stores that I buy hardwood from. We're going to be using SAE fasteners, and we're going to talk about some products in Home Depot, which is an American store. So let's talk about actually buying wood, because a lot of people find this confusing. For fine woodworking, you get wood from a hardwood store, and when you go to buy the wood, it's what's called RW and L, which means random widths and lengths. So the only dimension the shop sorts the wood by is its thickness. The length and width are random and often irregular, and we're not going to be using dimensional lumber or wood that has been milled for construction purposes, like 2x4s and 4x4s, which are sold in a fixed length. So you go to the specialty hardwood store because this wood has been milled and dried for applications like fine furniture. If you don't have one locally, you can get hardwood shipped. Also, people trash on Home Depot, but woodworking got really popular during COVID, and Home Depot has a lot of RW and L hardwoods now, and it seems nice and dry to me. So in the store, the boards of wood are going to be divided up by their thickness according to the quarter system. The quarters represent quarters of inches in thickness before any surfacing, so as the board comes off the saw at the saw mill. A rough or RGH 4/4 board will be roughly 1 inch thick because it's 4/4 of an inch. Oftentimes the boards are surfaced, meaning that they remove the rough saw mark so that you can see the grain and figure. That process removes material, so a surface 4/4 board might be something like 3/4 of an inch or 7/8. So you're going to see 4/4, 6/4, 8/4, 12/4, and 16/4. Sometimes you'll see 10/4, but that's rare, and oftentimes you'll see 5/4, which is the only typical odd number. Think of it this way as a rule of thumb. If the board is surfaced, it will be roughly 1/4 inch shy in thickness of what is advertised, so to speak. And if it's rough, you're going to have to do the surfacing on your end, and you can expect to lose about 1/4 inch of thickness during that process. And when I say expect to lose 1/4 inch, I mean if you take that board and immediately start surfacing it on your joiner. If you're going to cross-cut it into smaller pieces and then mill them individually, then you won't lose as much thickness because there's less overall surface area and less irregularity to contend with. And that's one reason that buying RGH or rough lumber can be an advantage. So we're going to talk about how to mill lumber with a joiner, planer, and table saw, but don't worry if you don't have those tools. You can still build high-end furniture without them. But you're going to want to look for wood labeled S2S or S3S, and you're going to want to get a board a little bit longer than what you're trying to make. Let's say 24 inches longer in total. S2S means surfaced on 2 sides. That means both faces are surfaced and the board has a uniform thickness. S3S means surfaced on 3 sides. That means that additionally an edge is surfaced and it's square to both faces. There is S4S lumber that has both faces and both edges surfaced, but typically they don't do this because they know you're going to rip the boards to the width you need anyway. Home Depot usually has S4S boards. Here's a helpful chart from a blog called Tyler Brown Woodworking. Just keep in mind there are some tools we can replace the table saw with, and I'll get into that later. By the way, I think I mentioned ripping and cross-cutting at this point. Ripping is cutting a board along its length, like this. And cross-cutting is cutting a board along its width, like this. Some other terms to know: a crook is when a board is warped along its edges, but the faces remain parallel planes, like this board. It's referred to as crooked. A twist is when the planes are all warped and the board is slightly helixing, like fusilli pasta. This is a twisted board. A cup is when the board cups into itself along its width, like a snowboarding halfpipe, and this board is called cupped. A bow is when the board cups into itself along its length, like a bow. It's common. Bow is more likely the thinner the board is, so this 4/4 board is badly bowed. It's still very usable if you're cross-cutting it to make shorter components like table legs. Those terms aren't interchangeable. They all refer to those specific conditions, but they're all examples of wood warp, and the term warped applies to all of it. Bows and cups are common. They're not a huge deal. You can remove that during milling. Crooks and twists can be a bigger issue, but because the end grain is where the wood soaks up moisture, it often occurs in the last 10 or so inches of the board. And that's why I'm suggesting you get boards with some extra length if you're not going to be going through the milling process. So sometimes what woodworkers are looking for is a well-quartered board, and this refers to where in the tree trunk the board was situated when it was being milled. Well-quartered comes from the term quarter sawn, and that's a type of sawing that a sawmill might do. So if you just take lateral slices of a tree trunk, you end up with a bunch of slabs, and these are technically called slabs. It's a way of making the most out of the tree, and it's also the easiest for the sawmill to do. It's called flat sawing or live sawing, which is where the term live edge comes from. But because the slabs are going to have two sides of grain pulling in opposite directions, they're all going to develop warp, and they're all going to take forever to dry. That's why big slabs are expensive, because they're prone to warp, so they require a lot of surfacing, and when they flat saw timber for this purpose, they have to cut extra thick, and they can only get a few slabs from each log. So they'll cut the slabs into boards which are more stable, and this is a form of plane sawing. Another form of plane sawing is where they'll do something like this. And this is just to avoid having these really skinny pieces. Now imagine a tree trunk cross section as a pizza, and then you cut it into quarters and cut a strip out of each slice from the tip outward toward the apex of the crust. This is quarter sawing, and the strips represent the 4 boards that are basically what fine woodworkers are hunting for. Because of where these boards were situated in the tree when they were milled, they're the most dimensionally stable boards that will come from this log. As for the rest of the pizza, there's a few different ways to try to make the best use of it, and likewise there's a few different ways a sawmill might execute quarter sawing. So in this example, you get 4 of these really nicely quartered boards per log. In this example, you get 8 relatively nicely quartered boards, and this is a little bit more efficient. In this example, which is called rift sawing, everything is perfectly quartered, but that's the most wasteful. Even in this plane sawn example, there are 2 perfectly quartered boards per log if you cut down the pith. In this plane sawn example, nothing is quartered. This is common, and a lot of the wood in your store will have been milled like this, but it's not a huge deal if you're getting a bunch of boards glued together in a panel. Later on, I'll talk about alternating end grain direction during glue up, and that's how you make a panel just as dimensionally stable as quarter sawn wood. So sometimes you'll see quarter sawn wood separated in the store, and that means the mill specifically quarter sawed or rift sawed that tree, and they bundled that material together. That stuff is expensive. Typically we're talking about white oak, and that's not what I mean by hunting for quarter sawn boards. I'm talking about literally digging through stacks of normal stuff that might be plain sawn and finding accidentally quartered boards and paying less for them. You can identify a well-quartered board by looking at the end grain. It looks like this, but a lot of times they'll paint the end grain of each board to mitigate warp. So you'll have to rely on looking at the long grain, which might have figure, like the rays in the case of this oak. Figure isn't grain, it's features that run opposite of the direction of the grain, and it's expressed most in quarter sawn wood. There are other factors to consider, namely you might want to avoid knots, but you might also like them or think it's cool when you fill it with epoxy like this. You have to pick what you're going to prioritize when you're shopping. If you're going for a big conference table and your glue up consists of a bunch of boards, then probably prioritize matching the grain of each board. If you're going for a little floating shelf, then probably prioritize stability so it doesn't warp on the wall. You might want the grain to match so closely that you can't tell there's a glue seam, or you might like the contrast of not doing so. The exterior perimeter of the usable part of the tree is called sapwood. It's lighter and softer than the interior of the tree, which is heartwood. Oftentimes boards will include quite a bit of sapwood, and you might not like the color differentiation, or you might want to embrace it design-wise. You might even pick theoretically inferior wood because the grain seems interesting to you, like this coffee table I made. That's the cool thing about woodworking, is that you kind of develop a taste in what you're looking for when you're finding materials. Alright, so you bought some boards and you gotta mill them so you can make your panels. The first thing you have to do is joint a face, but you can't just arbitrarily pick a face to joint. So here's how a joiner works. It's like a giant upside down hand plane. And in this image, the dude is using a hand plane to create a straight plane on this board. So now we'll flip it upside down. Imagine the hand plane is big and it's wide enough so we can surface an entire face of a board. The red is the infeed surface, the yellow is the cutter, and the green is the outfeed surface. The blue is the direction of your movement. The outfeed surface is precisely at the height of the cutter, and the infeed surface is parallel but lower. This is adjustable depending on how much you want to take out. So you need to start by placing a face down on a flat surface and checking if there's any rock. If there is, this means that the end of your board are cupping away from the flat surface. Again, the joiner is a big hand plane. So if we put our cup facing away from the plane surface, the blade can follow its curvature and you might be removing material evenly, but you won't actually be creating a flat surface. So now let's extend the surface really long like you would have on a joiner and face our cup down into the machine. The cutter is going to take a slice off of each end and it's going to repeat that process until you actually arrive at a flat surface. So if you have a rock, flip the board upside down and joint that side. Before any joining, I'm cutting off any excess from the boards I'm using for the top part of the bench, and this gives me less overall surface area to deal with on the joiner. Then I mark the face of each board that had less rock and I draw these pencil lines so I can see where I'm removing material. Then I start taking passes on the joiner, shallow passes for hardwood, and you can see that I still have some left to remove right here and right here. Put these little check marks here so I don't send that face through the planer. Before we head to the planer, I need to join an edge. We need to start first by making sure the fence is square. Before we were just flattening a face so the fence wasn't relevant, but now that we have a flat surface, we can square up our fence and run the flat surface along it. The result is an edge that is perfectly perpendicular to the face. The edges are just like the faces. If you have a crook, make sure you're not jointing the wrong side. When I have S3S stuff like this and there's no crook, I just joint the side that's already surfaced. And that way when I go to the table saw, it's super obvious which edge needs to be ripped off. So now we'll surface the remaining face on the planer. The planer relies on a perfectly flat surface running along its table because unlike the joiner, the cutter is on the top. So that's why we had to joint the face first. Turn the wheel a quarter turn at a time when you're using hardwood, and if you've got tear out, just try sending it through in the opposite direction and it usually fixes that. So now we can rip the remaining edge on the table saw. The table saw's fence is already square, or at least it should be. So our flat face is going to glide on the table, and our edge that's perpendicular to the face will ride on the fence, which is perpendicular to the table. And that's why you have to do it in this order. I'm ripping everything an 1/8 inch heavy here so I can do another saw blade pass to get rid of some burn, because mahogany likes to burn. That's what this is African mahogany. Definitely watch a table saw video for safety if you don't have a lot of experience on it. The basic safety thing is to not push too hard into the fence. If you push hard enough, you can force the fence out of alignment, and when it swings back, it will pinch your work, causing kickback. This is also where we're ripping the boards to final width, hopefully, so you need to rip them accordingly so that your panels end up the correct width. So here's what we did. Imagine that this messed up shape is our piece of wood. So with the joiner, we made this one face flat, and then we ran that flat face along the fence, making this edge square. Then that flat face rode on the table of the planer, and the cutter of the planer made this face both square to the edge and coplanar to the jointed face. Then with the table saw, we selected an overall width to rip to. We squared everything up in the process, and this is what we created. So if you don't have a joiner and planer, it's just a matter of digging through the boards at the store. You're gonna want to get S3S or S4S material, and you're gonna want to get boards with some extra length so you can cut off the ends, which are more likely to have warp. Inspect the boards for warp, but in any case, we can use a certain style of clamp to make sure everything is aligned during glue up, and I'll show you how in a bit. A track saw you can use in place of a table saw for ripping edges. You can even use a framing saw and a guide rail as shown in this YouTube video by Mellow Pine Woodworking. Your blade probably isn't square to your base on your framing saw, unlike a track saw, but that's okay because when you rip, you can alternate which face of the board the base rests on and glue up your pieces like this. When you're starting out, it's best to select boards that your joiner can accommodate. So if you've got an 8-inch joiner, don't buy anything wider than 8 inches. There are workarounds, but you'll have to either rip some width off, and taking a warped board directly to the table saw can be sketchy. Or you're going to have to do this whole operation where you remove the blade guard on your joiner and you make a jig to surface both sides on the planer, as shown in this YouTube video by Jay's Custom Creations. Also, if you've got an underpowered table saw, it's going to cause a lot of burns in hardwood, and these burns are really difficult to sand out of lighter woods like maple and oak. Burns are comparatively easy to sand out of mahogany and walnut. This machine has power, but I'm getting burns here in this mahogany because it's a shared workshop and they usually keep a crosscut blade on this saw, and there's no riving knife, so my board is pinching the blade. If it were my own table saw, I'd probably keep a riving knife. It's a little safer, but I'm really familiar with this saw. So here's the difference between rip and crosscut blades. The same thing applies for blades for your track saw. It even applies to Japanese pull saws. There will be a rip side of the saw and a crosscut side of the saw. So another aspect of milling is resawing, which you typically do on a big bandsaw with a wide blade. And you would do this, say, if the board foot price for a given material is better in, say, 12/4 than 5/4. So let's say your store has 12/4 walnut for sale for $8 a board foot, and you want a 1-inch thick panel, but the 5/4 stuff is $12 a board foot. Well, you know you can get 2-inch thick pieces from a 12/4 board on your bandsaw, so you buy the 12/4 stuff. So that's the other thing we should cover before we move on to glue ups. RW&L hardwood is sold in a unit called board feet. A board foot is a unit of volume that represents a 1 foot squared piece of wood that is 1 inch thick. So a 1 foot squared piece of wood that is 2 inches thick is 2 board feet, even though it's the same width and length. A piece of wood that is 2 foot by 6 inches wide that is 1 inch thick is a board foot. And a piece of wood that is 1 foot squared and that is 16/4 according to the quarter system is 4 board feet. The store knows what the rough size of the wood was. They round up. They're not actually getting calipers out and measuring exactly. So the way to calculate board footage is to multiply the length of the board by the width of the board and then multiply that value by the rough thickness, all in inches. Then divide that value by the number 144. At the place I usually go to, you just put your wood on a cart and you wheel the cart up to the desk and someone calculates your board footage and gives you a total. At other places, there's people like wandering around the warehouse asking if you're ready to get a ticket, and when you are, they calculate your board footage for you and they give you a ticket to take to the counter. Then you take your receipt back out to the warehouse guys and show it to them, and you're good to take your wood to your truck. At Home Depot, the board footage of every individual board is already calculated, and there's going to be a barcode sticker on the actual piece of wood, which is funny because anyone can just put a sticker from a small piece on a big piece, but don't do that. Also, if you don't have a truck and you just have a car, the hardwood shops will have a sliding saw station with a guy standing by it, and they'll cut any board you buy into any length you want. But you have to buy it first. You can't just bring the guy a board and be like, hey, can you cut this? I only want half of it. You have to show a receipt because you have to buy the whole thing first. Also, typically you're shopping in a showroom with boards stored vertically for your convenience so you can look through them. They have a ton more of the same material stored horizontally in the warehouse. So if you don't see any boards you like, just say, hey, do you have any more 6/4 maple in the back that I can see? It'll either be accessible and they'll let you dig through it, or someone should be able to pull it down with a forklift for you to at least see. If it's neatly stacked, don't go digging through it, but they'll probably let you pick from the top. Alright, so now let's glue our milled wood into panels. I like pipe clamps the best for panel glue up because they're strong and cheap. They also have these little flat feet which sit on a flat surface, making the pipes on all the clamps parallel to each other. They're cheap because you have to make your own. I like these ones from Bessie, which Home Depot has. Get 4 sets to start out with. Then you're going to want to go to the plumbing aisle at Home Depot and get some 3/4 inch black pipe. It's just regular plumbing pipe for low pressure stuff. It's threaded on both ends and you need one end threaded to accommodate the clamp. So get 2 10-foot lengths and have them cut them in half for you so you have 4 5-foot clamps. If you don't want 5-footers, just have them cut them in the smaller segments and then you need to have them thread the middle segments. The pipe clamps are what we're going to use to get our glue up started, but we'll need some other clamps to run on the opposite side of the panel to distribute pressure evenly. You can use more pipe clamps for this, but you don't need the feet, so you can also use quick clamps, or you can use parallel clamps, or just regular style F clamps. Then you'll need some short clamps to align the ends. You likely won't end up needing them, but I suggest having them. Short F clamps work. The cheapest would be C clamps. If you're using a clamp that doesn't have a rubber pad, softwood blocks can be useful to not clamp an impression into your wood. If you don't have any of the milling equipment, you're going to be going straight into a panel glue up, and you might want to look into what are called 4-way clamps. I like these on Amazon, which are sold in 2-packs. They're intended for you to screw into hardwood that you would have to mill. You don't have milling equipment, so we're not going to be doing that. Instead, you're going to go to the electrician's aisle at Home Depot and buy a product called Super Strut. These are sold in long lengths, so you'll have to cut them down. I don't think they'll do that for you in the store like they will with the pipe because they're galvanized. Then you're going to want to get these nylon strut cone nuts in 1/4-20, which they sell in 5-packs. They might not have enough in the store. When I made 4 of these clamps, I bought the whole stock and I had to go to another Home Depot to get the rest. Just make sure the thread is 1/4-20 because they also sell 3/8-16 and 1/2-13, and the electricians and HVAC guys digging through this stuff like to mix them up. Then you're going to want to get some 1/4-20 flathead machine screws. I think the correct length for these was 1.25 inches. By the way, a screw that has a flat surface on its head is called a flathead screw. This is not a flathead screw. This is called standard drive or slot drive, and a standard drive screw has a slot for a standard screw driver. This screw just happens to have a round head or a pan head. A standard drive flathead machine screw would look like this, and a screw with a plus sign which accepts a Phillips screw driver is a Phillips drive. Phillips refers to the drive mechanism and not the variety of head. So you'll need to move the components of the clamps around for each panel size that you glue up, and that requires you to loosen and retighten the machine screws into the cone nuts. So if you've milled your wood properly, I still suggest using pipe clamps over these because it's just a lot less setup time. YouTube user Matt Kuykendall has a good video on how to set up these exact clamps, and that's what I followed when I made mine. I like to cover everything I don't want to get glue on with wax paper. And you want to basically zigzag glue all over your joints with the bottle and then spread it with your fingertips. There's a lot of types of glue applicator tools if you're inclined. I don't like them, I use my fingers. And when you're starting out, I say be liberal with the application because it's better to have a messy cleanup than to not get a good bond and have to start your project over. I like Titebond 2, the blue bottle. It's what I'm used to, and you can work on your project the same day as long as we're talking about panel glue ups like this. If you're gluing a joint that's going to bear a load, then you might want to wait overnight and continue working the next day. Titebond 3, the green bottle, is the exterior grade Titebond, and this one will give you more working time if you're gluing up something tricky or complicated. It gives you about 10 minutes to get all your clamps situated, while Titebond 2 gives you about 5. I definitely suggest doing a dry clamp before you apply glue to make sure everything's going to align the way you intend. I'm using my 4-way clamps for the top part of the bench while my other clamps are being used for the bottom part. Like I said, you're going to have to loosen all your machine screws and retighten them according to your panel size. You're going to want to use some blocks so the clamps don't dig into your workpiece. And you can see here with the 4-way clamps, everything's aligned. You can leave your mallet in the drawer and you don't have to worry about dowels or dominoes or anything like that. And here's how to orient your panel glue up. If you've got all quarter sawn wood, just arrange the panels according to the grain pattern that you like. If you've got plain sawn wood and the end grain looks like this, then you're going to want to take a Sharpie and draw a curve in the direction that the grain is curving. Do this on all the boards and then alternate the direction of each board. Arrange the glue up this way primarily, and then secondarily you can select how you like your grain pattern. People often explain this as smiley mouth, frowny mouth, smiley mouth, frowny mouth. Sometimes when you're clamping, your pieces are going to move side to side because the glue is lubricating them. That's why we didn't crosscut yet, so we don't have to worry about that during glue up. But if for some reason you need your pieces to be situated in some precise way, you can use dowels to keep them aligned with a centering dowel jig like this. You can probably find a good guide on how to use them, but it should be self-explanatory. I like to unclamp the panel when the glue is just barely tacky still. And then I use this Kunz glue scraper. Expensive tool, but it is really worth it. Kunz are known for their spoke shaves, which are how Amish people make the spokes on their buggy wheels. Just scrape both sides and then you can clamp your panel back up if you think it needs more time. So now with the panel glued up, you can use a drum sander to sand it. At our shop we have a wide belt sander, which is really fast, but it does the same thing. So you can see it leaves a smooth finish and it flattens everything. If you don't have a drum sander, just go to town with an orbital sander. I like this Bosch, which I think is a copy of a Festool Rotex 150. They are tricky to find though. So if you can afford a Rotex 150, it is ultimately a great tool for this. It's gear driven, so it makes this really fast. It's intended to remove a lot of material quickly, and that's what I'm doing here. I'm ensuring all the glue seams are flat and I'm sanding out burns. I'm not finished sanding yet, but you can use a Rotex on orbital mode as a finish sander. You can also just use a regular cheap 5-inch orbital with some 80 grit. It's just going to take you a little bit longer. So assuming you want your ends to be flat and square to the edges, you can cross-cut them. Like I mentioned, I wait until this point to do this because it gave me the luxury of not having to worry about alignment in at least one direction during milling and glue up. Also, planers cause a condition called snipe on the ends of your boards. It's from the boards only contacting one of the two rollers, so just as it enters or exits the machine. It's usually only a mild inconvenience, but I'm going to cross-cut away all the snipe anyway. I'll use a track saw. It's like an upside down table saw where the track is the fence. You can also use a framing saw and a guide, or you can actually use a crosscut sled, which is a basic table saw jig, if your panel is narrow enough to fit in the sled and isn't so long that it's drastically overhanging the table. To give you some idea of how much material we lost during milling, we started out with 8/4 surface lumber. It was probably 1 3/4 thick. The top piece is now just over 1.5 inches, and the bottom is just under 1.5 inches. We lost more on the bottom because those boards were 24 inches longer. That's more surface area per given width, so more material was lost. And that's why I'm telling you to expect to lose 1/4 inch if you're going to mill yourself. So now you get to decide how you want to treat the edges of your panel. If you want them to remain relatively sharp, just start finish sanding, and during that process, you'll break the edge. That's where you gently break them over with sandpaper, but not so much that it visually removes the sharp appearance. You just don't want people to hurt themselves on it. If you want to treat the edges in some way, you can use a router and an edge bit with a bearing. Roundover bits give a roundover with a uniform radius like this. A thumbnail bit is like a roundover bit, but the profile is more parabolic than a uniform radius. You can use the flat part of the blade if you want, like this, and that's common for the underside of dining tables. Chamfer bits provide a profile with a chamfer at a given angle, like this. There are literally hundreds of router bit profiles to choose from, and if you want to get interesting, you can use bits intended for making picture frames or molding that can give you some wild profiles. If you're going to do a complex profile, your router bit might not allow you to take multiple passes, and in that case you need to learn the difference between a conventional cut and a climb cut. Because you run the risk of blowout on the two corners where you're transitioning from end grain to edge grain during a conventional cut. If you want a simpler profile like a roundover or chamfer, those bits allow you to take multiple passes so you can conventionally cut around the whole thing. Generally speaking, you want to avoid climb cuts because the tool can grab the material and run away from you. If you take your right hand and you place it around any corner of your panel, your index finger points in the direction that you'll move the router for a conventional cut. Router basics, for small bits, you can run them at full speed. For larger bits, slow it down. Also, if you don't know, never push your shank all the way into the collet, because it will vibrate back outwards. Watch a more detailed video on routers if you don't know what the shank and collet are. Here I'm just adding rabbets to the underside of the bottom part of the bench because the bench legs will notch into them. You're probably building a different type of piece, in which case you don't need to worry about that. By the way, the edge profile I'm using for the bench is a 3/16 roundover, and I'm doing it with my little cordless trim router. If you want a little trim router, wait until November because both Milwaukee and DeWalt usually have a buy 2 batteries get a free trim router deal for Home Depot's Black Friday deals. Just keep in mind that these can only accept 1/4-inch shank bits. They don't make a 1/2-inch collet for these, and that will limit the type of edge profiles you can do, but these are good for a first router. So with the panels crosscut, it's time to finish sand them, but first you need to take care of a few things. The first thing is to move your panel onto a soft surface like a moving blanket, because from here on out you don't want to get any scratches or dings on it. Then you're going to examine the panel for any dings and circle them with a pencil. I didn't have any dents, but if you do, you can steam these out with a soldering iron. You just get it real hot and put a wet paper towel over the affected area and introduce some steam, which will cause the ding to lift back out. It might not come all the way back out, but even so, it still makes sanding easier. You can't remove scratches this way because they're caused by an abrasion. You can only remove dings that were caused by an impact. Then we need to fill any cracks and voids. Small cracks and voids you can fill with wood filler. I like Timbermate as a traditional wood filler. I also like Mohawk epoxy putty stick, which is like a solid 2-part epoxy that you mix by kneading it and then you fill voids with it. It's way quicker to get to a sandable state, and in my coffee table video I go into detail on how to use this product. For larger stuff like knots larger than a gumball, it doesn't work as well. One quick way of filling these is to use CA glue or super glue, which companies like Starbond make in black, which gives you an epoxy filled type look. If you're using CA glue for this, just don't use accelerator because it will cause air bubbles. For really big knots or knots that travel all the way through the board, you'll need to use epoxy, which I've never really used. I just don't care for the process. It's not fun to me, so I pick wood that won't require me to use it. So watch other people's guides on how to best use epoxy. So my panels are ready to sand and I can start finish sanding, and my typical process is to start with my Rotex 150 on orbital mode. I start with 120 grit and then move to 180. For certain species like oak, I might start with 80 grit, especially if the wide belt or drum sander was burning it. Then I switch to my Festool ETS 125 and I do another pass with 180 and then move on to 220 or 320 depending on the finish. For this video I'm going to be using a hard wax oil finish, and the makers of these finishes usually recommend sanding to 180, but 220 or 320 is totally acceptable. If you can't afford a Rotex yet, I recommend that Bosch equivalent I mentioned if you can find one. I do recommend the ETS 125 for a finish sander, even for a beginner, because it really is the best finish sander Festool makes, because it has the smallest throw of all their sanders, and you will end up with a surface that has no orbital marks whatsoever. Most professionals prefer the ETS EC 125 because it has a brushless motor, and it's just overall a more pleasant machine to use ergonomically. You can get it in 2 different throw sizes, but the throw on the smaller one is still not as small as the ETS 125. So if you're going to be doing massive conference tables where you're sanding for hours, then yeah, get one of the 6-inch EC sanders and save your wrists. But if you can deal with some vibration and replacing a brush or two, then go with the ETS 125. It's much cheaper and it does an even better job. The ETS 125 isn't going to be powerful enough for you to do your initial 120 pass in a timely manner, so for this, instead of the Rotex, you can use any cheap 5-inch random orbit sander. If the only tool at your disposal is one of these sanders, then I recommend orbital sanding up to 220 grit and then going back to 180 with sandpaper on a block and sanding in the direction of the grain by hand. And then going back up to 220 by hand, because with these types of orbitals, there really isn't a good way of getting those orbital marks out regardless of what grit you're using. Also, if you've got a roundover, make sure to finish sand the roundover like this, just like you're breaking the edge. If you go like this, then you're going to be sanding flat facets into the edge, and you want to avoid that. So do this. My favorite paper is from Serious Grit. It's much cheaper than Festool Granite or whatever it's called, and it's just as good. They make paper for every hole pattern. If you have an air compressor, a pneumatic sander can be cool, but they're going to get your environment really dusty if you don't have good dust extraction, and they can be really powerful, so you got to be careful not to sand any impressions into your wood. Water popping is when you rub a wet towel on the surface of the wood and you wait for it to dry between each grit that you sand to. It's pretty important if you're using a water-based finish. I'm going to be using a hard wax oil, so it's less important, but if you have the time to do it, it's not a bad idea, especially if you're going to be sanding up to 220 or 320. So as you're sanding, you're closing the pores of the wood, and if you rub water on it, the fibers that absorb the water will pop outward, and this causes the surface to go from feeling smooth to feeling rough. But not all the fibers would have absorbed the water, and those fibers that didn't absorb it won't raise. So even though it feels rougher and it feels like you're going to have to do a ton of sanding to get it smooth again, you really don't. Regardless of finish, it's helpful because it kind of gives you a roadmap for progress when you're sanding the next grit. You sand the surface smooth, pop it, and then it will feel rough, and then as you're sanding, you know you completed that grit when everything feels smooth again, and then you can pop again. The reason it's important for water-based finishes is because if you don't do this and then you apply the finish itself will actually pop the grain, and you'll end up with a surface that's actually rough under the smooth finish. And it's not going to look right. It's still a good idea with hard wax oils because according to Rubio Monocoat's website, if the grain is closed too much, the product cannot penetrate as easily. If the product contains pigment, less product also means less pigment, resulting in a less intense color. In this scenario, water popping helps to open the wood grain, allowing for more of the oil-based wood finish to penetrate, resulting in more intense color. That's probably why they suggest only sanding to 180. They want you to get really good penetration so they can get a good review on their product. They don't want people finish sanding so much that they close all the grain and the wood won't accept their finish. Just keep in mind you have to wait for the wood to dry before you can continue sanding, so if you're trying to get something done and you're using oil-based finish, it's not necessary. I often use Osmo and I sand up to 180 without water popping, and it's still a nice finish. You can speed up dry time by blowing compressed air onto the surface. Also, you don't need to pop the end grain. Pretend this bundle of straws is our board and the individual straws are the wood fibers. If you get water into the end grain, it's just going to go into the straws and sit there. It's going to take forever to dry, and the end grain doesn't actually raise like long grain. Definitely sand in a well-lit area. It's easiest to see the swirls and sanding scratches under bright, cool lighting like LEDs. It's also helpful to take your piece out into direct sunlight if it's lightweight enough. For finish, I'm going to be using a hard wax oil. These have been pretty ubiquitous for like 5 years now, and they've pretty much replaced finishes like water-based and oil-based wipe-on urethanes and polyurethanes. Those are considered a little old-fashioned at this point, I think. There's a lot of hard wax oils on the market, but the two that I have the most experience with are Osmo Pollux, and specifically the 3031 matte finish formula, and Rubio Monocoat Oil Plus 2C. If you just want a natural finish on your piece, then go with Osmo. That's what I'm going to do here on this project. First, I either blow the panel off with air to remove dust, or even better, I use a tack cloth to pick up any loose dust. I used to use naphtha, but unfortunately in California you can't buy this anymore. It's the best at picking up loose dust and evaporating instantly. It doesn't get your fingers or gloves sticky like a tack cloth, and it doesn't linger like mineral spirits. I'm pretty sure naphtha is the same as Zippo fluid, but Zippo fluid would be expensive to use this way. I apply the finish with a white Scotch-Brite, just a regular white pad I get from the hardware store, and I keep the Scotch-Brite in the can when I'm done because next time I go to use it, the Scotch-Brite will be super saturated and it makes the can last a lot longer. I always start with the bottom or interior side of the panel, whichever is going to be seen less, and I just work a really good coat into the wood, wait a few minutes, and then wipe the excess off with shop rags. You need to be careful with oil-soaked rags. As the finish cures, it generates enough heat that it can potentially light the rag on fire, so a lot of people throw them in a bucket of water, and that's fine. I typically take the oil-soaked rags, I spray them with water, and I lay them out on the ground to dry, away from any wood dust. You want to finish the bottom first, then flip your piece over and finish the top side quickly because chances are you got some drips of finish on the edges. And if these drips cure too long, they'll cause a color anomaly, even when you apply finish to that edge. So I usually just take some plywood scraps that are clean and dust-free and just place them under the very edges of the piece. You can also buy painter's pyramids and just place the piece onto them. The theory is that because they come to a fine point, they'll cause only a tiny impression that won't be very visible anyway. The point is you just want to have good airflow underneath the panel as it's curing. Do the bottom first so you have a last chance to examine the top or outside before finishing, and sand if necessary, but make sure to get it dust free again before applying finish. Then finish all the edges, and you have to finish all the edges even if one or more isn't going to be seen, because an unfinished edge can absorb moisture that gets trapped under the finish, and that can cause cracks. If you want to use a hard wax oil and also add color, Rubio Monocoat will be the best choice. You used to have to stain first and then finish, and staining can really throw off the uniformity of your piece. It can produce a splotchy result or require blending because certain portions might absorb more stain based on either user error or just the way that piece of wood was. But Rubio Monocoat has solved that problem. It's another hard wax oil like Osmo, but it's a little bit more complicated to use, and that's why I typically go with Osmo if I'm going for a natural finish. But if color is what you're going for, then use Rubio. It has pigment mixed into the finish, and it comes in all these colors. A lot of them are named after woods, but don't think you have to use that color for that wood. For instance, feel free to use the mahogany color on maple. It would probably look really cool. It's a two-part system, so you'll need to mix the correct ratio of part A and part B, and then apply it with a white Scotch-Brite, just like Osmo. Some people use this little squeegee thing to apply it. I think Rubio actually recommends doing this, but I find I just have more control with the Scotch-Brite and I get less drips over the edges. It's called monocoat because they intend for you to only need to apply one coat, so you're most likely good with one coat, but it wouldn't hurt to add another, I guess, even though Rubio themselves claim, quote, a chemical reaction bonds the finish to the wood, and then a second coat can't bond to itself. With Osmo, in my experience, a second coat just gets rid of the dry feeling that a single coat tends to leave. It's almost slightly too matte with just one coat, but I've only really ever used the matte finish formula because it's what they have in my store. They do make a satin and gloss formula, and maybe those don't have that issue. With Osmo, you're dipping the Scotch-Brite back into the can periodically, and over time the finish will turn the color of the wood you're using the Scotch-Brite on. So say if I use a can on like 6 different walnut projects, the finish is going to turn walnut colored, and I'll probably go and get a new can before I start a maple project. With Rubio, you're mixing the two parts in a dedicated container, so you won't have that issue, but you will have waste. For maintenance, Osmo makes a cleaner for surfaces finished in their oil, while Rubio makes a soap concentrate that I think also works pretty good. So you made some panels so you can now make furniture because you can construct furniture out of several panels, like I did for the vinyl record cubbies. That's just panels I glued up. Some of them have rabbets and there's some dowels holding everything together, but there's no complicated joinery there. It's just walnut I milled and glued together and finished. You might want to add metal hardware to your piece, and if you just want to know the woodworking side, you're in luck because there's a lot of fabricators and fab shops that offer a lot of different style table legs and bases and brackets and stuff. This is flowy line design, for example. Etsy has a lot of options, and you can also just walk into a fab shop with a drawing of what you want, and they can help you refine the design into something that they can make for you. But if you, like me, had a problem where you wanted a specific type of hardware that you had a vision for and you couldn't find it, then you're going to want to know how to make it yourself. So that's why it's handy for someone even primarily focused on woodworking to know how to weld. I'm not a welding expert. I have a lot more woodworking experience than metal fab experience, but I know enough to teach the basics, I think. So there's a lot of different welding processes, and the one I'm going to use here is MIG, or metal inert gas welding, because it's the best process for a workshop or a garage environment. TIG, or tungsten inert gas welding, is also good for a workshop or a garage environment, but it requires a lot of skill and patience and practice to learn, whereas MIG welding you can learn in one day. Flux core welding is basically MIG welding, but without gas. The wire itself produces a shielding environment. It causes a lot of splatter and it will fill your shop up with smoke. It's better for outdoor use, for a situation where wind is going to blow away your shielding gas anyway. And then stick welding also doesn't require gas, but it's more for job site and construction environments. But you want to make furniture, so you're probably in a shop or a garage indoors with a roof over your head and hard floors, so you can have a little welding cart to wheel around with a gas bottle on it. It's not going to be an inconvenience to you. I should also note here we're talking about using mild steel as our material. We're not going to be welding with stainless or aluminum. Buying metal from a metal supplier is a lot easier than buying wood because there's nothing to sort through or inspect. All the pieces are the same pretty much, and they will also cut things to length for you once you buy. So if we're going to weld things together to create something, we need to make the parts that need to be added together, and for that we need to first make a cut list. I normally use 1-inch square tubing for these benches, but I'm using 1.5-inch square here just because it's going to make this process visually easier to understand. So we can draw up the dimensions of what we're trying to make in CAD or on paper, and the outside lengths are what we need to cut our parts to because we're going to miter them, at least the actual main rectangle part. So now we need to execute our cut list. We've got this big horizontal bandsaw in our shop, and we also have this cold saw, but I'll show you affordable saws you can use in place of these. So this is my little horizontal bandsaw from Wen. I'm going to rip through this cut list on the cold saw, but I saved some cuts for this saw to show you that you don't need expensive equipment to cut your steel and start fabricating. There's a bunch of different versions of this Chinese saw, and I think they all come from the same factory. I know the clutch version is popular, and same with the grizzly version. People call these hem saws because I think the brand H-E&M brought them to market first. They might be exclusive to Europe. This Wen version is about $340 right now, and I went with the Wen because Home Depot is a distributor and you can get a protection plan, which it's a simple serviceable saw, but the one concern with Chinese machines is the motor, and I'll talk about the other reason why I picked this version when we talk about my welder in a bit. There's other tools you can use to make both your straight and mitered cuts with tube steel. If you already have a portaband like this laying around, you can get a base that converts it into a horizontal bandsaw. Harbor Freight has one for like $100. It's a copy of a Portaband Pro, which is American made, and as much as I don't like intellectual property theft, $380 is a lot to ask for a simple base like this, but it's at least worth mentioning who invented it if I'm going to suggest that you buy the fake version. Probably your cheapest option is going to be to get an abrasive cutting saw like this, which you can find for $40 on Craigslist. They're cheap, and the cutting discs are cheap, and they're fine. They are noisy and sparky, and they just feel kind of sketch in general. An improved version of this is a dry cut evolution style chop saw. The blades are expensive and you have to get a feel for how fast to cut through material to extend the blade life, and they're really only for mild steel. They are spark free, but they're still really noisy. They're also not like an SCMS or what a woodworker might call a chop saw, which is actually a sliding compound miter saw. The head of the saw doesn't rotate, rather the vise does, so if anything gets misaligned mid-cut or the force you're using to cut with is slightly off, it can grab the work and do violent stuff, especially once the blade gets dull. The little orange bandsaw here, on the other hand, has a stationary vise and the saw moves according to your needs, so you can actually set up a mitering station for metal in your workshop with this, just like you would see in a wood shop. So when you're working with a cut list, you need to start with the longest lengths first, and here I've set the order in which I'll cut by length. The plus signs just indicate to me that there's a hard minimum there. So let's say I have 3 10-foot lengths of tube and my cut list is 2 at 7 feet, 2 at 4 feet, and a 3 at 1 foot. So I'll start with the shortest lengths first, and I'll cut 3 1-footers from this stick. Then I'll move on to the 4-footers, and because I can fit one on that stick, I'll cut it from there. I can't fit another 4-footer on that stick, so I'll cut it from this one, and now I'll move on to the 7-footers, and I can't fit a 7-footer on this stick. So I'll cut a 7-footer from the final stick, and now I'm stuck because I can't get my other 7-footer from anywhere. So now, same scenario, same stock and same cut list. I'll start with my longest length first, and I'll get a 7-footer from this stick. I can't fit the other 7-footer on there, so I'll cut it from this stick. And now I can't fit the 4-footers on either of those sticks, so I'll cut both from the final stick. I can fit a 1-foot segment on that final stick, and then I'll get 2 others from one of the segments I cut a 7-footer from. So our cut list is complete, and we have all this nice usable rem for a future project. So here I am just ripping through the mitered cuts. You want to cut everything to length first before you miter because it makes being accurate easier during this step. You just line a speed square up to the end and you scribe your 45 degrees. I suggest keeping different squares and tape measures for metalworking and wood so you don't transfer cutting fluid and metal oil to your wood projects. My favorite tapes for metal are Milwaukee wide blade because they don't deflect at all. And for wood I like Fast Cap old standbys because they're cheap and they have a little pencil sharpener built in, and I'm always using a pencil when I'm woodworking. When you're cutting your miters, you want to make sure you're cutting them so that the seam will be on the inside surface of the piece. Square and rectangular tubing will have this seam from where it was welded in the factory. You can see it on the top of this tube, and round tubing will also have this unless it's DOM or drawn over mandrel tubing. And you just want to do this because the seam can be noticeable, especially if you're using patina or wax as a finish, but they can also be visible under paint or powder coat. So now I'm just doing that final miter cut in my bandsaw, and you want your blade to fall directly on the scribe line when you're using a bandsaw, unless you have a piece that has a hard minimum. Say something out of your control is off, like for instance the blade isn't tracking perfectly through the material. We have a rectangle here, so that error is going to compound 4 times, and your overall rectangle dimensions are going to grow somehow. It seems weird, but it's not like a table saw where the side of the blade should perfectly contact a line. You can use tap fluid, or you can also use a stick lubricant like this. So you can see here the cold saw cut is just a little cleaner and nicer looking than the bandsaw cut, but they're both perfectly good miters. You're just going to take a little longer on the bandsaw. So with all the parts cut to length and mitered appropriately so the seam is on the inside surface, we need to prep the pieces for welding. First, you're just going to quickly take a towel and wipe off most of the oils and cutting fluid, just getting it relatively dry, but you don't need to go crazy here because we're going to clean it more thoroughly before we weld. This is just so we don't gum up our flap discs. Then we need to bevel our edges with a grinder. I use 40 grit flap discs. Flap discs are kind of wasteful because they're made of these flaps of sandpaper, and you're never going to use any of the abrasive that's tucked away deep in there. But they're just good, both at grinding down welds and for blending, and I do recommend 40 grit because you can both grind down welds quickly and achieve a nice finish with the same disc. They're all basically the same brand to brand. They all sell them in the same types and with the same kinds of abrasives. The blue colored abrasive is a zirconia based abrasive, and that's the one that I use, and you're probably going to find type 27 and type 29 most readily. T27 is flatter, T29 has a subtle angle to it. You can use either for these purposes, just try both and see if you have a preference, but I can switch back and forth between both types and just adapt my blending technique with no problem at all. So you're beveling here both to deburr the sharp edges of the tube, but also because you want a little channel for your wire to go into. And we'll get into how welding works in a second, but your gun's going to shoot wire out of it, depositing material into this void. If there isn't a good chamfer on both pieces, your wire isn't going to penetrate as well, and you'll be depositing material just onto the outside of the steel. It won't form as good of a puddle, and the joint might be weaker. Do this to both mitered edges fairly thoroughly. You don't want to grind too much away. As a rule of thumb, grind at a 45-degree angle and grind half the material away. This tube is 11 gauge. It's about an 1/8 inch thick, so we're shooting for about a 1/16 inch wide flat facet. And then for the corner edge, just kind of soften it. Obviously, because it's an outside corner, we can't make a channel, but we can soften this edge, and that will give us an easier time depositing material right here. Now thoroughly clean your material with acetone, and then throw your acetone soaked rags away, far away from where you're going to be welding, because the sparks from your welder can ignite them. Also, don't keep an open bottle of acetone around when you're welding. So you're going to jig up your material into your rectangle so you can weld them up. I'm using my fancy fixture table here, but I'm not going to be doing anything on it that you can't do with an ordinary steel workbench or table. Fixture tables make jigging things up easier, more accurate, and more easily repeatable. They can be expensive, but if you want to have some of their capabilities in your shop on a budget, look for what are called welding fixture carts, which are like fixture tables, just more lightweight and portable. Harbor Freight just recently came out with a 24-inch by 36-inch fixture table for $169. It's not a cart, but you can probably figure out a way to get it on wheels, and it's the perfect size for little bench legs like this. And you can make bigger things when you're using a fixture table. You're not limited to the size of that table when you're fabricating. You can absolutely have parts of your workpiece overhanging the ends and move it around as you weld different parts of it. It comes with a bunch of fixture accessories as well. A lot of fabricators just have a regular steel workbench, and you can also weld on the ground if you need to. I don't recommend welding on a wooden workbench because there's a lot of sparks flying off the gun when you're MIG welding, and it's just going to ruin a wood surface. Unlike milling hardwood, there isn't really a correct order of steps in which to fabricate a rectangle. There's different ways to skin a cat, but here's my current process I use. So take half the rectangle and make an L, and I'm just going to tack this inside corner, then tack this outside corner, and then tack this one near the bottom, but not on the bottom because then we'd be welding it to our table, just a little bit north of there. The tacks are just little zaps to hold the pieces together. We're not ready to put real heat into this steel. We just want to hold it together lightly, so if something isn't correct, we can just break it apart and correct the issue. This is just temporary work holding. So here's those tacks. So then I'm going to jig up my two L shapes into my rectangle and tack those corners the same way. Don't worry about the clamps and squares I'm using yet, we're just talking about the order of operations. Once you get the rectangle tacked up, you need to clamp with downward force so that the piece doesn't deflect when you weld it up for real. So I'm just going to be filling this void with wire in a straight line, point A to point B. Some people like to use this whip and pause technique, which looks like this. And then some people like to draw little cursive E's over and over again, but you don't need to worry about these techniques right now. We're just going to keep it simple, and we're going to connect the dots point A to point B. I like to push the wire into the void rather than pull the gun along like this. And that's the result. That's all of those welded up. You want to let that cool down for a minute and then start grinding those welds down. So I come in like this with my disc at an angle and I get most of the weld grounded down. And then when it's getting close and I'm starting to touch the tubes themselves, I level it out and I grind the rest of the weld down, keeping the disc flat. Then I blend into the tube so that you don't have a visible low spot. We're grinding these all down because we want to flip the rectangle and weld the other side, but we need it clamped downward again, so it needs to be perfectly flat. Everybody has a different way of holding the grinder. I like to use my dominant hand to push down and control it. I don't like using the handle, but you might find it useful. So clamp it downward again and you're ready to weld the other side. So that's all of those ground down. We gotta weld the outside corner now. You can weld it like this, but there's not really a good place to rest your left pinky on, so a lot of times I do this instead. Resting my left pinky on the table and letting the corner overhang, I pull the trigger before I contact, dragging the nozzle down, this time pulling, and gravity just helps lay the weld into the corner. You're gonna be left with this little piece of wire because you'll pull the trigger as you're sweeping down, and you can just grind that down real quick. Then I grind all those welds down. This is how I do it, basically. Easier to just show you than to try to explain it. If you feel like you don't have good control, you can clamp the piece downward, and then just make sure to bevel the corners so they're not crazy sharp. Then I just blend the rounded corners like this. So here's me trying to do whip and pause. You can see I'm not that good at it. Here's my cursive E's, a little bit better. These kind of techniques are called MIG like TIG, and I think it's just people trying to entertain themselves when they're welding and trying to make their weld look clean and sexy like a TIG weld. People say it gives you better penetration, but I'm convinced it's just because it slows your pace down. So here's an example of a bad result, and this happens if you run out of gas and you keep welding. I didn't actually run out of gas, I turned the gas off to demonstrate this, and this is called porosity. Then this is how to fix it. You just grind your weld down like normal, and you'll see all these pits where oxygen was bubbling because there wasn't any shielding gas. So now take a cutoff wheel and recreate the channel. This is Milwaukee's 3-inch cutoff tool, but you can also switch to a cutoff wheel on your grinder. Get a 4.5-inch type 1 wheel, and then if there's any holes left over, you can open them up with a tiny drill bit, a pointed burr on a die grinder, or something on a rotary tool. In this example, my shade was set too dark on my helmet and I messed up connecting the dots. That didn't actually happen, I just closed my eyes and I tried welding it. It's the same process to fix it. Grind it down and then recreate the channel and try again. And this is what your rectangle should look like, all ground down and blended. Sometimes you'll see people's grinds look like this, and this is because they're not using a flap disc. Notice that we didn't weld the inside armpits. It just looks better if you don't do this, but you would want to do this if it were for an outdoor piece of furniture or if it were a structural component of something. So now I'm just jigging up the non-mitered sections like this. Then I weld them up. And then I grind them down. The 11 gauge steel is easier to learn with than 16 gauge. 11 gauge tube has a wall thickness of about 1/8 inch, so it's thin enough that you can weld with an affordable welder for personal use using a standard 120 volt receptacle. And it's thick enough that you can slow down the speed with which you're moving your gun and actually get an understanding and feel for the MIG welding process. I like a corded angle grinder, but you can use a cordless one if you already have a lot of batteries for it. So you might have noticed the yellow tool on my table. Those are called MIG pliers, and they have recessed cutters, and when you butt your nozzle up against them and cut your wire, they give you precisely the correct length to get proper gas flow in your next weld. They also have these large serrations, which is for removing the nozzle if you need to maintain it. And that's what the exterior serrations are for. Splatter can build up in there and restrict your gas flow, and you can remove it with these. The small serrated section is for removing your tip, which sometimes you need to replace. There's also this hammer feature which you can use to knock off splatter that sticks to your material. And then the indent on the tip is for actually pulling or drawing wire. I use these ones from Stronghand. I usually hook the chain to my belt loop, and they're just always in my back pocket when I'm welding. Make sure you get the Deluxe Plus model, which is the MIG version. So now I'm just sanding the areas we ground down smooth with 80 grit. It's not like finish sanding wood. This only takes a couple of minutes. It just gives the surface a nice texture and appearance, and I'm just using a regular 5-inch orbital. You want to get no-hole paper. You don't want metal getting sucked into the tool, and steel dust doesn't linger in the air like wood dust. It just settles. Mirica Bulldog is my favorite paper for metal. So here you can see the difference between one that hasn't been sanded and one that has been sanded. I'm adding this cross member because this is the longest one of these benches I've made. It's 8 foot long overall. I'm going to add mounting plates for the legs. Because the legs sit so close to the edge of the wood panel, I don't want to put screws there. I want to move them inside some. I'm going to use 1/4 inch hot rolled flat bar for the mounting plates. Flat bar is either hot rolled or cold rolled. The cold rolled stuff is smoother and more dimensionally true, but it's more expensive. Hot rolled stuff is covered in this stuff called mill scale, which you can see forming in this image. It's a rough surface, but these plates aren't going to be seen. If you're having your parts powder coated, they're going to media blast all the scale off anyway. It's really costly to have single items powder coated. If you're going to be fabricating things frequently, wait until you have a bunch of things to bring them, and then bring them all at once, and you'll get a better price. I already cut, beveled, scribed, center punched, drilled, and countersunk all my pieces, but I saved one to show you the process. You would do each step of the process in series to save time and not have to switch out your drill bits with every part. I'm going to pre-drill here with a number 7 drill. Number 7 is the same as 3/16, and you want HSS or high-speed steel twist bits in a jobber length. Then I'm going to jump up to a 5/16 drill. Use cutting fluid to extend the life of your drill. 5/16 will be the correct size for both 1/4-20 flathead machine screws like I'm using, and number 14 wood screws if you're screwing directly into the wood. So now I'm going to use an HSS countersink so our flathead screws are nice and recessed. Countersinks come in a variety of angles, and we're using an 82 degree countersink. You'll see them marked in the hardware store either as 82 degree or 41 degree. And that's what you use for SAE fasteners. 90 or 45 degrees is for metric fasteners, and there are other angles for other purposes. Just make sure you're getting the right countersink for the fasteners you're using. The flutes of 82 degree countersinks taper outward to 1/2 inch, which is the diameter of the heads of both 1/4-20 machine screws and number 14 wood screws, and you keep countersinking until you've used the entire flutes and you have a little lip on the top of your hole. That way your screw head is going to sit perfectly flush with the surface of the part. Some fab shops, when they're fabricating or making metal hardware for furniture like this, they'll create a slotted hole rather than a rounded hole. And I'm not doing that for this piece for a few reasons, but the reason they do this is because wood panels swell given atmospheric changes. Metal hardware doesn't swell, so if the wood begins to swell, it will put tension on a fastener going through a round hole. So if you're in a climate like Michigan, where you've got hot, humid summers and dry, cold winters, and you're making a big dining table, you might want to have slotted holes instead of round holes. So I just got my pieces placed here where they're going to go and get welded up. With these guys, you don't necessarily want to do a straight line because it can be hard to control the puddle. These are called fillet welds. So we'll just tag this surface, this surface, this surface, this surface. Just go back and forth. That's all I'm doing here, just a couple of inch-long stitch welds. You don't need to weld all the way across because that would be way too much heat for this, and it would be a waste of wire and gas. So on the other side, I can see the heat transfer from those welds, and I'll just hit it from the other side in those same spots, and then I'll grind those down. So I'll go over the equipment I use for welding. First of all, there's the table. If you have a fixture table, wipe it down with acetone when you're done. And then give it a good mist of WD-40 so the surface doesn't start to rust, and it's going to be nice and splatterproof next time you use it. My table is thick, so I ground to it. This way I can get all my welding done without having to reposition the ground clamp. If you have a thinner table like the Harbor Freight one, the heat can warp the table, so I suggest clamping your ground cable to the workpiece itself. The squares you saw me using are from Fireball Tool. They make these in either cast iron or aluminum. I have the aluminum ones. The cast iron ones are more durable and heat resistant, but you can accidentally weld your work to them. You're going to want these locking clamps to go with them. You can get them with a swivel pad or without, and I suggest getting a few of both. I definitely suggest the Fireball squares or a cheaper equivalent, or even making wood ones over a magnetic square like this. These will become useful for tacking stuff up, but for full welds, the heat can overpower the magnet and throw your piece out of square. So they're best used once you understand their limitations. If you don't have a fixture table, F-clamps like these are the best for clamping stuff downward. For PPE, you're first going to want a welding hood or helmet. I used to use a fixed shade one like this for over a year. It's a huge pain in the ass because you have to position your gun, then take your hand off the work and flip the shade down, and then pray that your wire is going to feed where you want it. Then my wife saw me welding with it and she was like, "Don't they have an electronic one that does it for you?" And then she got me this from Yes Welder. It's auto darkening. It's the Welding Helmet Pro 2.0, and it has all the typical controls. It's got a shade dial, a delay dial, a sensitivity dial, and cutting and grinding mode so that sparks don't trip the auto darkening. I often wear a respirator. Lincoln makes one that fits under a welding hood. A lot of people like to wear a welding cap to prevent your scalp or hair from getting burnt by sparks. I just wear a backwards baseball hat. You're going to want a burn-resistant jacket, and you're going to want to get gloves so you can actually handle your material. I like TIG gloves because you just have a little more control with them. If there's other people around in your shop, get a welding curtain so you don't give them flash burn. At my last job, I was on a saw working on a cutlass, and my coworker was next to me doing some MIG welding. Obviously, I wasn't staring directly into his arc, but it being in my peripheral vision gave me flash burn. And what that is the UV rays from the arc are damaging your eyeballs, and basically when you lie down to go to sleep at night and you close your eyes, it basically feels like the back of your eyelids are 80 grit sandpaper, and the little subtle movements your eyes make when you're trying to fall asleep are incredibly painful. It's really just not chill and not a fun time. Likewise, if you're not wearing a jacket, and I have welded plenty of smaller pieces like this in a t-shirt, but it will give you a sunburn primarily on your non-dominant bicep because that's what's closest to the arc. So we'll talk welders, but first of all, I recommend watching this video by Tim Welds. He'll show you more comprehensively how MIG welding works and how to set up a machine. So for my welder, I picked the Lincoln 215 MPI. MP stands for multi-process because this welder can do MIG, TIG, flux core, and stick processes, and it's spool gun ready, which is how you MIG weld aluminum. The I stands for inverter, which this is a newer style inverter machine rather than an older style transformer machine, and that helps them package everything smaller and more lightweight. I wanted a machine that would allow me to work into TIG and spool gun aluminum welding, and if I ever need to take the welder somewhere outside of my shop, I can do flux core and not have to worry about gas. So the other reason I picked it is because Lincoln, and at the time of uploading this is still true, offers a $400 factory rebate that applies to anyone who buys this welder new from one of their distributors. The Little Wen bandsaw was about $400 with the 3-year protection plan from Home Depot, so I spent my rebate on that, and I think the combo of this welder and this saw are an excellent way to start a small fab shop for $2,000. The 215 MPI has this cool feature called Ready Set Weld, so we tell it yes, we're MIG welding with C25 gas. Everything's plugged into where it's supposed to go, and yes, our gas is connected. We're using .030 diameter wire, and our steel is 11 gauge. You can only do 10 or 12, but I'll go with 12 and dial it up if I need to, and it sets the machine for you. It also has this arc effects feature, which shows you what your puddle will look like given the material parameters you gave it, as you adjust your wire feed and voltage settings. If you want to stay under $1,000, I think the Everlast Cyclone 212 would be good. This one only does MIG and stick, but it's spool gun compatible. The Lincoln Easy MIG 140 would probably be good if you know you're going to only want to use a 115 volt power source. It is a transformer welder, so it's a little big and heavy for its output, but that's how they keep the price low. It's about $670. For my cart, I got the Vulcan 350 pound capacity cart from Harbor Freight, and for $110 it's great. There's these little retaining tabs that secure the welder, but they were placed too short for my Lincoln, so I bent them down and bolted down a piece of aluminum so my welder doesn't slide backwards. Your main consumable is going to be gas. You get it from a gas exchange place. You go in and you buy a gas bottle, and you pay the price for both the gas and the bottle, and then every time you come back, they swap your spent bottle for a new one, and you only pay the cost of gas. Get a bottle that's at least 60 cubic feet, otherwise you're going to be going back after every project. For MIG welding, you typically get C25 or 75-25 gas. It's 75% argon and 25% carbon dioxide. For mild steel, you want to get ER70S wire and probably in a .030 diameter. And you're going to need corresponding .030 tips. I like the .030 Ts, which come to a taper so you can fit them in tighter spaces. So now we're going to finish our metal hardware. Powder is the most costly, but it requires no labor on your end. You can also paint. I'm sure you know how to use a rattle can, but it's laborious and it's less durable than powder. I'm going to apply patina and clear coat, which is both cheap and easy labor, and I'm using Black Magic from Sculpt Nouveau, which is nice because you can apply it cold. You just shake the bottle and pour into a paint cup. This is probably enough for this project. Then you just apply it with a maroon, brown, or gray Scotch-Brite, depending on how dark you want. You just pick a surface, apply it, and do your best to blend the drips. If you get a hazy effect, you can get rid of it with white Scotch-Brite. This is a highly acidic product, so don't get it in your eyes and wear gloves because it will turn your fingernails orange. Then I apply Sculpt Nouveau Clear Guard, which is a clear coat for metal, and it dries really fast. Sculpt Nouveau makes a ton of patinas in all these colors, and they also make waxes, but I have less experience applying waxes. All in all, you are going to have some anomalies. That's part of the reason you're using this finish. It's called patina because it's supposed to make the metal look aged or weathered and give it character. It's an acid that oxidizes the metal in a controlled manner. It's like a thin layer of rust, but it rusts black rather than orange. You do need to clear coat the same day, otherwise it will genuinely rust and turn orange. So now we're done and we can attach our hardware to our panels. I like these threaded inserts. They're just a little more accepting of force than a wood screw, and you can see here for the 1/4-21s we need a brad point bit that's between .295 and .343 and a 6mm hex key. Sometimes these say softwood only, but you can use them on hardwood. So I've got an appropriately sized brad point bit, and I'll just use some tape as a drill stop and drill the holes for our inserts. Sometimes I use super glue or 5-minute epoxy to secure these even more. If you do that, you'll want to re-tap the holes. So now we'll just drive them in with the 6mm hex key. Nice and flush. I'm using wood screws for the middle. They're so far in, I'm not worried about the force. The inserts just help if someone bumps into the bench or some impact happens to the ends of it. I'm applying a little paste wax like min wax or tree wax to the threads to prevent splitting as I drive them in. Also do this if you've got stainless fasteners because it will prevent them from breaking. So I've made a few of these benches now, so I know that if I got my rabbets correct, this is the part where I get to hear a very satisfying thud. So I basically showed you how to make furniture, but we didn't actually talk about furniture design, so I will go into that briefly. First of all, you should know that there are standard heights for things. There's a standard height range for a dining table, a sitting bench, a workbench, for a desk, for a coffee table, for nightstands. Just double check that what you're designing fits within these ranges. Second of all, when designing, I suggest to incorporate the golden ratio whenever possible. It's basically a ratio that makes everything look pleasing to the eye for unexplainable reasons. Photographers and car designers like to call this the rule of thirds because it's roughly 1/3 to 2/3, but the number 3 is unrelated to how the golden ratio works, and it's not actually thirds. An example is, say you're designing a sitting desk and a client wants a single drawer for pencils under the desk. It's got to be a small drawer because most of the room underneath needs to be for leg room. But don't just arbitrarily be like, I think this drawer should be 7 inches. Actually calculate what the smaller portion of the ratio would be to the overall length of the desk and make your drawer that length. The panels we use for this bench are just big rectangles, but maybe you want to add some more curvature or interesting shapes, like this coffee table I made, which is more mid-century modern than modern. This is where template making comes in. You can make a template to route a shape into things using a flush trim bit or other types of router bits, and the tools that are useful for making templates are: number 1, French curves. These are for artists. They're basically these things full of parabolic contours that you can trace that were designed according to the golden ratio. They're curves that are literally calculated to be pleasing to the eye. But after French curves are Forstner bits, which are like brad point bits that bore holes of larger diameters. A jigsaw, a scroll saw, or a benchtop bandsaw. A spindle sander, you don't need one big and industrial like this. A belt sander, a disc sander, or some combination of the two. And finally, a drill press, or even better for furniture making in some circumstances, is one of these called a drill guide. You have only 2 options with these: a really high quality one from Rockler for $200, or a crappy one that's $15. Like I mentioned previously, you can join panels together with joinery. I just didn't want this video to go on forever, and this specific project didn't call for it. Box joints you can do with your table saw or a router, same with rabbets and miters. If you're making something like this, I suggest gluing big panels and cross-cutting them for the small pieces so you don't have a million glue-ups. This is also what you would do if you want the grain to waterfall or continue over an edge like this. Finally, we only covered hardwoods, but you can make a lot of really amazing furniture out of sheet goods like plywood. The thing is, for advice on working with plywood, you don't want to take advice from a fine woodworker. I'm not good at edge banding, and I feel like every time I look at a sheet of plywood, my eyeballs just scratch through the outer veneer. There are people who are professionals at making these products look really good, and those people are cabinet makers who are different from fine woodworkers. So anyway, I hope this helped or gave you some new information in some way, and you can make some cool furniture this year. Thank you for watching, and subscribe if you're inclined.